This is a basic hybrid connection. We are looking at a glowing data stream bridging a physical server rack on your premises directly to a single workload in the cloud. At this level, hybrid connectivity is straightforward. You point A to B, and traffic flows. But enterprise cloud footprints do not operate at the scale of a single workload. When an organization scales up to dozens of distinct, isolated Google Cloud projects, each managed by different teams with different security requirements, this basic model fractures. If you build point-to-point connections for every new project, you generate a tangled mesh network. This complexity quickly creates routing loops, obscures visibility for security teams, and creates a massive administrative burden that will eventually fail under its own weight. To avoid that failure, we will map the precise architecture required to build a highly resilient, highly scalable hybrid connectivity model on GCP. We will build an enterprise-grade hub-and-spoke topology from the ground up. We will evaluate the physical transport layer, implement dynamic BGP routing in the control plane, and establish a centralized security topology. Moving from a mesh to a hub-and-spoke model reduces the total number of connection points you have to manage, allowing the network to grow without a linear increase in administrative complexity. Let's start with a blank canvas. Here is a clean schematic showing an on-premises data center on the left and an empty Google Cloud region on the right. Our first requirement is bridging this physical gap. The fastest way to establish that bridge is site-to-site HAVPN, routing an encrypted IPsec tunnel over the public internet. However, throughput hits a strict 3 gigabits per second, and internet reliance introduces volatile paths and unpredictable latency. For data-heavy workloads requiring predictable low-latency performance, we bypass the internet entirely. By utilizing dedicated interconnect, we establish a direct optical link. This thick connection provides up to 100 gigabits per second of dedicated throughput, backed by SLAs, completely circumventing internet volatility. But the physical link only dictates the bandwidth ceiling and wall latency. A dedicated pipe is fast, but it lacks the intelligence required to actually manage and direct traffic at an enterprise scale. If we program static routes into this connection, the system remains fragile. A static route has no awareness of network health. If a physical path fails, the traffic simply drops. To solve this, we must introduce dynamic routing into the control plane using Google Cloud Router. Zooming in on our GCP region, we establish a host project, which acts as our hub VPC. Inside, we deploy the cloud router. It connects to your on-premises routing equipment using Border Gateway Protocol, or BGP, establishing a continuous dialogue between the two environments. It is crucial to note that the cloud router does not sit in the actual data path. It does not inspect or forward your packets. It strictly manages the routing tables. Through this BGP session, the cloud router dynamically advertises your available Google Cloud subnets to the on-premises data center, while continuously learning the prefixes of your on-premises network. Integrating dynamic BGP routing upgrades a passive pipe into an intelligent network that identifies the optimal active path without requiring human intervention. We now have a fast, intelligent connection. The next step is utilizing it to serve multiple distinct cloud workloads without recreating the tangled mesh we saw earlier. To achieve this, we deploy a shared VPC architecture, which natively enforces a highly controlled hub-and-spoke model within Google Cloud. In this topology, our existing host project acts as the central hub. It securely houses the cloud router, the interconnect attachments, and all core network infrastructure. We then deploy smaller service projects, attaching them directly to the hub as spokes. These newly attached service projects function as isolated deployment environments. This is where developers actually deploy virtual machines, databases, or Kubernetes clusters. This enables strict separation of duties. Admins control the hub, while developers access specific spokes. Tracing the path, an on-prem packet crosses the interconnect, enters the hub VPC, and distributes down the spoke into a workload inside Service Project A. The architectural efficiency is clear. Traffic from your data center ingresses into Google Cloud exactly once, at a single, heavily monitored checkpoint. By isolating workload administration while centralizing network control, shared VPC provides a structured framework that prevents the unmanaged sprawl of individual hybrid links across every project. To qualify for Google Cloud's strict 99.99% availability SLA, our architecture must eliminate absolutely every single point of failure. This requires provisioning at least 2 distinct interconnect connections, ensuring they terminate in 2 physically separated edge availability domains. We mirror the links, running 2 solid interconnects into distinct zones, connecting to dual cloud routers for redundancy. If a primary link is severed, the BGP session instantly withdraws routes, immediately rerouting all active packets over the secondary line. This centralization also establishes a powerful security posture. Because all hybrid traffic is funneled through the central hub, security engineers can apply unified, hierarchical firewall policies. Every packet is inspected against these universal rules before it is ever allowed to touch a developer's spoke. True enterprise reliability is not a feature you toggle in a console. It is the physical result of combining dual link redundancy, dynamic BGP routing, and a centralized security choke point. Here is the entire topology: dual redundant on-premises routers, dual dedicated interconnects, and dual cloud routers sitting within a highly controlled shared VPC host project, branching cleanly out to isolated workloads. Before deploying a hybrid network of this scale, an architect must verify 5 critical requirements. First, capacity and latency. Mathematically verify your bandwidth and latency constraints to determine if you can utilize the high agility of HAVPN, or if you require the strict SLA and raw throughput of Cloud Interconnect. Second, topology. Confirm that you are utilizing a shared VPC. This enforces the strict separation of network administration from workload deployment. Third, dynamic routing. Audit your cloud router BGP configurations to guarantee that routes will automatically withdraw during a link failure. Fourth, redundancy. Map your physical topology against Google Cloud's specific requirements. You must utilize dual links and distinct edge availability domains to secure the 4.9's SLA. And fifth, security. Confirm that hierarchical firewall rules are actively inspecting all ingress and egress hybrid traffic exclusively within the host project. The goal of cloud connectivity is to completely abstract the complexity of the physical distance. By strictly enforcing these architectural patterns, the network boundary ceases to be a bottleneck. The Google Cloud Edge transforms into a highly resilient, seamless extension of your own data center.